Okay. Thank you very much. Thanks for the chance to speak here. And I think since the conference is coming to an end, we'll take this opportunity to thank the organizers for hosting the conference. Okay, so this story I'm going to talk about starts with this notion of stability condition. So, measurement. This is also short for on the article. And there was a previous version from 2014 on the archive, and 1 year later we got updated and stronger results, which I'm going to talk about today. Okay, so it starts with this notion of a stability condition, which is your description. Stability condition is some way to talk about stability in stable objects in a triangulated category. And and what it is essentially kind of axiomatic approach. You don't have some, the name says condition, but really you don't really specify a condition for something to be stable. Stable objects are part of the axioms. So what this is it's some sort of data which specifies a stability condition is some, so for each real number, which is the phase, there's going to be some collection, additive subcategory, of semi-stable objects, C phi, full additive subcategory. So essentially just some collection of objects, isomorphism classes of objects, C phi and C. And these are just called, by definition, the semi-stable objects. Of phase phi. And then the second piece of data is something called the central charge. It's essentially just an additive map Z from the Grothendieck group of the category K0 to the complex number additive. This thing is called the central charge. Some terminology which is motivated from kind of string theory origins of this whole definition, which is due to Michael Douglas, who wanted to find some sort of axiomatic framework which describes behavior of D-branes, superconformity theories, supersymmetry. So, yeah, so this is these two pieces of data, and all this has to satisfy a number of axioms. I have to be really careful here. I already myself a bit. But luckily the podium here comes stocked with band-aids already. First conference I've been to. So this all has to satisfy some axioms, which I don't want to list all of them. Some 5 axioms. Maybe the most significant, and which wasn't there yet in Douglas' picture, but which Bridgen introduced is, so one of them is this these generalized Adamasi multiplications. Which says essentially that if you take any object in this triangulated category, then it's going to might not be semi-stable, it might not be contained in any of these subcategories, it's unstable, but then there's a unique way of constructing, so building it up from semi-stable pieces. So This is saying that for all objects x, you can see we have some sort of filtration in the triangulated sense. Just a bunch of cones, x0, x1, xn. And so there's some triangles here. The cone of that map is some object AI. So there's some triangle A1, AN. And all these A1 through AN are all they're all semi-stable, so they contain one of these subcategories, and their phases should be decreasing strictly. So if you're thinking about vector bundles on a curve, then this is something we proved that every object has this kind of filtration, but here we're sort of requiring it as an axiom. That, for any object, I can build it out of these semi-stable ones. And so this kind of thing, only if it exists, then it's unique. Okay. And then there's a bunch of other axioms to compatibility. Maybe I'll mention them later. Okay. So it's a slightly bizarre definition. Why do we have the complex numbers here when the category might be anything defined over any field? So the definition really comes out of string theory in a sense. But then there's a very nice theorem here which justifies in a bit why this is mathematically interesting. Which then so if I look at the space of all these kind of structures, stuff of C, this is the set. Maybe I need to assume that the category is essentially small, something, and the set of all stability conditions. Yeah, sometimes, always, I won't really need it in this talk, but sometimes we fix also variant where we fix some thing we think of as a term character from K0 to some gamma, which is gamma is infinitely generated abelian group. Which is free, so some map here. And we want C to factor through this. It's really only defined. It depends on this perhaps a term character going to homology. It could be any choice of this map. Finitely generated factors through this map CL. Okay, and then so if you look at the set of all these things, then well, you can introduce a topology here. That's some topology. In fact, it comes from a metric space structure also. It's a natural metric here. Which, yeah, maybe. Well, which is saying that essentially this thing here has to move continuously, this central charge map up here. And what you get is some sort of jumps in the Haiden filtration. Okay, but it has some topology, and then the statement of this theorem is that the forgetful map you can go from this and just forget the collection of semi-stable objects and just go to space of all central charges, swan and gamma to C, so C to Cn, essentially, that this is a local homeomorphism. So what it means intuitively is that if we doesn't mean to be a local homeomorphism. If we deform the central charge in some small neighborhood, we change this map slightly up here, then there's some kind of unique new collection of semi-stable objects which are close to the original point. So we see kind of wall crossing going on. Objects become unstable or real objects stabilize. But there's a canonical way to do that. Okay, and so what this theorem immediately gives you is that this has a, just use these as local charts. Just put some complex manifold structure on this space. Of stability conditions. Okay, so it's a complex manifold. But it has all this additional structure also. So where it gets interesting is it has, first of all, it has an action. Moduli space of stability conditions. First of all, has an action of the universal cover of GL plus 2R, rotation preserving maps R2 and R2. The universal cover. And this group acts essentially by just, it acts on the central charge by composing that, and it will change phases of semi-stable objects, but it won't change the actual collection of semi-stable objects. So you have the same semi-stable objects, you act by an element of this group, but this just changes the central charge. By composing central charge with element in here. That's kind of the first group that's acting here, and another group that's acting naturally is a group of autoequivalences of this category. Autoequivalence up to natural isomorphism. This also acts. And perhaps one of the motivations for introducing this space of stability condition is you want to understand this group here of autoequivalences. You have some space where it acts, then the idea is that this will help clarify the structure of that. Okay, and then another structure that's naturally present is a complex manifold that's actually but it also comes, since you have this stability, it comes with some wall and chamber structure. And people here probably know this kind of walls. I mean, so some walls could be dense, so it could be chambers could be irrational numbers, very tiny, depending on whatever the category is. Walls might be dense. And so what are these walls? This is just where some sort of object loses its stability. Where its collection is C by changes. Some object becomes stable or unstable. Okay, so it's got all this structure. In a way, it's still a bit mysterious. If you just take some category, let's say, non-derived category of some sufficiently high-dimensional variety, it's not even known if this space is empty or not. So even constructing one stability condition can be quite a difficult problem. Yeah, so what I want to talk today about is that all these sort of spaces, well, it was realized that you have very similar kind of moduli spaces in a similar structure in a different geometric context, and that of moduli spaces of quadratic differentials. Look at some moduli space of pairs C, C5. C here is some compact Riemann surface. And phi here is a quadratic differential. Which is perhaps meromorphic, or slightly more general, transcendental. Mainly, there's always another way to think of all this. You can think of this as some surface with flat metric. So the integral of the square root of this quadratic differential. So I use some local charts. So this is equivalently, these are some flat surfaces, and the precise term here is a half translation surface. What that means is some surface with a flat Euclidean metric. And it's the monodromy is just contained plus minus 1, so half translation. A translation surface would be completely trivialized monodromy, so here. So, monodromy. The structure group has been reduced to just plus minus 1. And plus, so these things would be kind of trivial. What makes them more interesting is that you allow some conical type singularities. Okay, and they move in some finite dimensional surface has finite type topology. Then these things form some sort of moduli spaces, and again, so these here have some action. Action of this group GL plus of R. And they have again a wall and chamber structure. What the kind of walls are. Well, if you have a flat metric, you can look at geodesics on that surface, and the walls are whatever these geodesics are. Essentially straight line. It's connecting two of these conical points. Something called a saddle connection. Then what can happen is that some conical point just breaks along as you move in the moduli. This breaks along some other conical point. And these are the walls in that space. And so the question is, so two moduli spaces here which have some similar structure, and how are they related? So the natural conjecture that was made here by Fukaya and Solomon, I think. Here that this moduli of these flat structures have translation surfaces. This should be identified with the stability condition on the Fukaya category, or some version of the Fukaya category of the corresponding surface.
Is there anything special about Ka?
Yeah, so if you have a quadratic differential, that means it's going to be a half transition surface.
No,
If you have an Euclidean, Yeah, it really, so this doesn't work, or at least I don't know how to make it work if it's not half translation.
Does the moduli space of some fraction translation, does it always have a wall and chamber structure, or is that also a thing that makes sense?
Yeah, so you can remove here this half translation hypothesis, just look at arbitrary restriction. Also has a structure, but I don't know what the interpretation is. It doesn't look like it's stability or something.
What about like just translation, not half translation?
Oh, just translation surface would be an abelian differential, so that's a special case. Yeah. So half translation is either, you could also have trivial, so the quadratic means it's half.
Are there any walls in the straight, when it's just a translation surface?
No walls you get for any kind of flat surfaces.
So including the case you don't put the word half.
That's true. Yeah, I could give this whole talk without here half and here instead of quadratic differential, abelian differential.
And it would still be interesting talk.
Yes, yeah. But this is the more general case, if you want. It's pretty much the same talk. Yeah, but yeah. So you could here consider more general modulus cases of just translation, just flat surface, don't put this restriction, and I don't think that it has any interpretation of this form. But who knows? Okay, and so here is some version, and more precisely here this will be some partial Fukaya category. It's punctured surface.
The surface means Riemann surface.
Yeah, it's two real dimensional. So it's a big word for something which is essentially some combinatorial thing. Real dimension 2. Okay, and so well, that's the idea, and the actual theorem we can prove is if you like some n is somehow some suitably defined modular space. So yeah, first of all, maybe fix. I should say what the input is. So some kind of marked surfaces. Or what is needed to define these kind of categories. Input in both of these sides to make sense is can then be there's different ways of how to define this. You can take a compact surface boundary plus some marked points. Could be both on the boundary and in the interior. So this is S, TS, plus marked points and S, maybe on the boundary. And the plus the whole thing needs. So this needs to be a graded category. It needs to be C graded. You can easily see that if I have a Z mod 2 graded category, so shifting twice is the identity, then there's not going to be any stability conditions on it with this definition.
What if shifting twice is just, what if you have something periodic and you just think of shifting twice as some additional operation?
What do you mean?
Well, I mean, I'll ask it.
So, well, yeah, so for the purpose of this talk, I need these categories to be C graded, which means, right, how do I make this category C graded? I need to choose some grading of S, which essentially means I'm choosing some section of the projectivized tangent bundle, i.e. foliation essentially. So this will make this category f of s C-graded. Yeah, so that's it. That's the entire. If I have one of these kinds of guys, then both these sides would make sense and are defined, and the theorem is that if M is this will be a space of like a Teichmüller version of the space of flat structures. Like I'm marking, fixing some surface. So M is space flat structures, half translation structures. And on S. S is one of the, that's all this data. F of S is partially wrapped. Fukaya category over some field. There's no restriction on the field at all. Then, yeah, so partially wrapped here. Didn't really, experts will sort of have an idea of how they get it.
Wrapping spots that are points to boundaries.
That's the idea, yeah. So if all the marked points are in the interior of that surface, if there's no boundary, then this is just a random category. What the idea is I have this boundary components, marked points, and then curves will need to end at these marked points. Or, I mean, there's two versions, or the curves maybe.
Which one is it? Do you swap it? How is it into the points, or do you somehow wrap until the points?
It's a convention, yeah. So, yeah, either way, it will be the same category. So an example, if I have the annulus, and there's one marked point on each boundary, then I want this to be this should be mirror to dv of v1. And if I didn't have any, if I had, yeah. Okay. Unique way of how to define this. And sort of, well, many ways again, since this is, so these things kind of essentially some, S here is some, not so F should have some boundary. So I want, yeah, so kind of some non-degenerate assumption that these set of marked points is not empty. Then there's essentially no symplectic geometry here, right? So it's an open surface. This category is some rigid thing. So it has also some kind of combinatorial definition. It's kind of combinatorially defined. For example, based on this Lagrange skeleton, this ribbon graphs. Will be global sections of the cosheaf over a ribbon graph. But yeah, I don't want to really go into detail because it's not important precisely how to define it, but that it is, or what do you expect, that its objects are curves, and they have this gradient.
You're not going to prove some sort of statement by showing that equation stability conditions interact well with coordinates?
No, that's because all these, the geometric structure I have, the flat structure, is not compatible with any ribbon graphs in general. So that's not an approach you can take. So the space of stability condition, it doesn't have any nice property with respect to coordinate mechanics.
Oh, I see.
Yeah, so this is just all theorem. So what's the actual theorem? Then the map. So there is a canonical map from the space M of S to space of stability conditions on M of S, and this is almost an isomorphism. It's kind of not, I don't know, it's some bianalytic onto its image. Which is some union of its components. So the only thing I don't know is maybe there's this moduli space here has some other components which they have nothing to do with these moduli spaces. I don't know any example where that would happen, but it's not something that I can disprove at. But to expect is actually to be the same, not quite there, but it's almost so. It's some number of components you take in here and you get this space. Okay. So that sort of answers this conjecture here about how wiring stages can be. Maybe to have a concrete example. That wasn't all too precise here about all the definitions. I think there's a canonical way of doing it all. If we let S use a n type category, so it's this with n marked points. All on the boundary. Then the category of that this ideal category of a one-dimensional Lambda-Weinberg model, which is just this is just representations in derived sense of an AN quiver. It's a quiver where you have n vertices, this is some orientation of an AN Deacon diagram. I mean here that it's a bounded derived category. So it's that category, and then the space stability condition on that some. So it turns out just to be Cn, but what's its more intrinsic description in terms of some quadratic differential. Here there's no complex structure because we're on CP1 genus 0 case. So these will be some kind of quadratic differential, which are exponential types, so they're e to the power of some polynomial, degree n plus 1. So e of z, some polynomial, complex coefficients, n plus 1. And look at the space of all these, and then I mod out by automorphisms of C. And yeah, here I need to mod out this to be true. I also need to mod out auto equivalences of this category. This is some C times C2. So it's either C mod 2 or just C. Some covering space. The definitions of this orbital cover. And the actual space has a complex manifold stability conditions of this. It's just C power n. Okay.
n plus 1 mark points
It's the n.
n+1 mark points on your disk.
Oh, sorry. N. Thanks. Okay, so I want to say a bit more about the geometry here. What are these quadratic differentials? It's the flat geometry. So yeah, there's always two perspectives, either in terms of the flat metric or in terms of the quadratic differentials, complex analytic point of view. Quadratic differentials. This is one way of describing what this space here more or less is. Some pairs mentioned C phi, compact complex surface, and phi. So what are the possible restrictions on these quadratic differentials? Well, any kind of meromorphic differentials are allowed. But as in this example here, you can also do something slightly more general. You can have so that points where locally this quadratic differential has a transcendental singularity, some e, so c minus n times g of c dc squared, positive n, and some meromorphic g.
So are you basically saying you allow somehow irregular rank 2 connections?
Yeah, that would be a nice. So sections, these kind of guys are sections.
And n is basically the number of large points on this. How to say it?
So if the connection has a simple pole, then you get sections will be just meromorphic differentials. And
how do the number of points on the circle correspond to the degree of the?
It's just this n here. So these kind of points, you imagine that
So it's like usual correspondence because number has the same as in the Fukaya correspondence between irregular connections of points on the circle.
I don't know anything about that one here, but yeah. So you think of points where this happens are the boundary components or n markers.
You like draw the Stokes directions.
Yeah, but I'm not sure there's a kind of kitchen system picture in this case. So these things are their solutions to some sort of connections with higher order poles.
Oh yeah.
So you can also think of this guy here in the exponent. It's the Landau-Ginzburg potential locally, but it's only locally defined. Yeah, so you can sort of mix. So you can have this in any order of zeros and poles, any meromorphic. Plus you allow these kind of things. And by saying allowing all these differentials, they appear in one of these spaces anyways. And so the ones with the same combinatorics, so all the guys which are in the same space and less have the same order of zeros, number of zeros and poles and so on. So the surface here, right, from one of these guys you get a surface like here, or just these the zeros. Poles correspond to mark points in the interior. And one of these points where you have this transcendent singularity is e minus n squared correspond to a boundary component n mark points. Boundary S1 n markings. the grading is just the one coming from the quadratic differential. So the grading is the horizontal foliation of the quadratic differential. So those vectors where on which phi is positive or negative. Okay. So each one of these guys you can associate this input surface here, and all the ones which produce the same surface belong to the same moduli space. Yeah, so this is sort of one point of view. Just using complex geometry, and then you can all maybe the more natural even point of view is in terms of the flat metric. So I have this pair C5. I want to remove kind of the bad points, 0 minus similarities. Of phi. And then there's a flat metric on this, just the absolute value of phi. It's locally Euclidean, and this has local Euclidean charge, which is integrate the square root of this thing locally. Okay, but if I remove all these similarities, then it's going to be some surface which is not one. Take the completion of S. Take the metric. Completion of S. Just add some finite number of points. Conical similarities. And that's kind of the point of why I'm not, by restricting to this class of quadratic differentials. So this sort of class of quadratic differentials ensures that when I complete this flat surface, I don't get something crazy at infinity, but just I'm adding some finite number of points. Some tameness condition on the flat structure. Okay, and so now how are these singularities connected to the quadratic differential? So if I have a 0 of phi of order n, then this produces a conical point with co-angle 2 plus n times pi. You can think of this as I'm taking 2 plus n copies of the half plane and I'm gluing it together. It's a first order 0. This is the structure. These are geodesics. So here's the flat. What I'm drawing here is the horizontal foliation. So these are all straight lines in the flat metric. And I've glued 3 copies of the half plane in case n equals 1. And so where you only have 1 copy of the half plane is for a simple pole. So this produces a conical point. Co-angle pi. And so higher order poles, they don't produce any similarities. The surface is already complete. But one thing which higher order poles means that the corresponding flat metric has infinite area. So in the simplest example, it's a second order pole. It's like the square of a first order pole of an abelian differential. So flat structure is just the usual flat cylinder. Looks like an end of a flat cylinder near that point. Okay. And then about is kind of easy cases. The tougher cases where you have this transcendental singularity. This minus n gz squared. Then if I complete this metric, it's going to produce n conical singularities, which got a limiting case here where I don't include some finite number of half planes, but I include a countable number. So I get n conical points with infinite cone angle. So imagine this picture, but instead of gluing in more and more half planes, the whole thing looks like I'm taking the Euclidean plane, puncturing it, and taking the universal cover of that. It's like a helix. And it produces these conical points. In particular, in the case for AN category, the space is going to look like a disk, and then there's n plus one of these points at the boundary. Okay, that's kind of the flat geometry picture here. And we're interested in, so what are these? The first thing I kind of have to say about this map in the theorems, and there's some canonical map, how do you produce a stability condition on such a flat surface? This map M of S stability condition. Heuristically, or sketch how this works. Well, first of all, I need to identify there's some lattice gamma, which is just K0. I'm just going to map CL as the identity, gamma is F of S. And it's going to be identified with kind of H1 of S relative to the marked points. But here, yeah, there's some kind of twisted version of C. And twisting with the two orientations of the foliation. It's a twisted version of the usual locally constant system of C. Twisted version by orientations. The grading orientations of foliation.
This piece is compatible with Colimit, right?
Yeah. So, and that's kind of a way how you would prove this, or one way to prove that these two things are the same. Because right. And so these two things being identified, this map C, it's defined by essentially taking periods of the one. So Z is something which takes K0 C, and it maps some curve alpha, which is an object in this category, or some homology class in here. F of S has some class in H1. It's going to be mapped to the integral over square root of phi alpha. And because here I'm twisting with this locus of the orientations, this square root makes sense. It's two choices of orientation of foliation, or the two choices of square roots of the quadratic differential, so this kind of thing makes sense. So this is this central charge map. And then, so the other piece of data is these semi-state objects. And they're just kind of what you guessed, they're just a finite GP6, essentially, on this flat surface.
which thing wasn't compatible with the colon?
The space of stability condition definitely not compatible with coordinates.
Like your stable objects is somehow defined locally, I guess they locally live for the finite amount of times. That's certainly compatible with colon.
Well, it's local in what sense? It's local not on the Lagrangian, but on the entire surface, right? And the Fukaya category is not something which is local on the surface, but local on the Lagrangian scale. I don't know. If, or we can talk.
Yeah, okay.
But like, it's not even functorial, like if you have a functor between two categories, there's not even a map on the space of stability condition.
Yeah, it's not much clear. Yeah, so semi-stable objects, so the C5 will be essentially finite length geodesics. Plus some local systems of phase 5. Essentially they're slope, but since they're all graded objects, it makes sense to see what their phase R is. Plus some local system vector spaces. C and on C. So it's just two things that really happen. It's either a saddle connection, a rigid object, it's connecting two conical points. It can also happen that it's looping back this homoclinic guy, which is looping back to the same conical point. Or the other thing is that it's a closed loop. So it's moving in some non-parameter family. But yeah, so if I want to state this in this way, if I allow any local system, then I need to identify all these, or choose the exact representative with respect to some exact structure. So these are the two kind of objects. So this is C5, and then all this data sub-theorem before this other theorem. This is that this data satisfies axioms of stability conditions. And the crucial thing to show here, what's not so trivial, is this, what I mentioned, the Haiden property. You're saying that for any object in the Fukaya category, you kind of find some collection of these semi-stable objects, so closed loops, saddle connections, and kind of building using cones, I can build this object out of these ones. And why that's, so we need this FMS, the crucial theorem that's used to show this is a classification of objects in this category. And this is here defined in such a way, it's not just any curve of the local system. A priori, this needs to be closed on the cones. The stability conditions to make sense, is to have triangulated structures. Closed. So what the content of this theorem is that a priori you have some collection of curves, and then you have some linear algebra data, which is some kind of bounding cochain maybe, which is defining some formal cone, iterated cone in this category. But then what you show is that you can always get rid of this, you can always reduce it in the end to a geometric object. So all objects geometric, meaning that so they come from possibly immersed curves plus local system vector spaces.
5 minutes.
Okay, so this is something which is very particular to the one-dimensional case, the two-wheel-dimensional case. So this in particular, it's saying that this is a tame representation type. So there's at most one-dimensional families of incompressible objects. Very particular to the slow-dimensional case. But once you have this, then you can show how an Arsenal property, well, it's something you have to show for every object. If you understand every object like as an inverse curve, then it has some geodesic, broken geodesic representative, and you get these pieces out of that. So rough sketch on how to show this property. Start with some object here. Then using this classification, give some indecomposable, give some connected inverse curve. And then taking the geodesic representative. Some broken geodesic representative. Some collection of finite geodesics. And these are these factors in the Haiden definition. So we show that these are associated with some semi-stable objects by definition. And then you show that filtration here, that there's some extension of these objects which gives you back the original X. So it's roughly a sketch of how that goes. Okay, but that only produces, so that's all of this work is just to show that we actually have a map here, and then to show that it's bianalytic onto its image, and so the image is closed also. The most difficult point here, so it's clear that both have the same dimension, here these two groups are the same. Also that this injective is not too bad, but then the most difficult part of this statement, which is the main theorem, is to show that the image of this map is closed. Stability conditions. It's closed. And so what does it mean if we have some sequence of stability conditions, and we know they all come from some flat structure, and if they converge with respect to this topology on here, then we should also have some corresponding flat structure here. It's somehow saying that we have convergence in here, then we have convergence back here. And so that means we're producing a flat structure just from a stability condition. And here, so my main technical way to show this is using these Voronoi decompositions. And this will denote cell decompositions. In some way, if I have a flat surface, it has a lot of different triangulations, but there's some canonical things you can do. These cells. And then you can show that this sort of structure, this extra thing, essentially converges to something else. And that's the main step of this this argument, that it's closed. Okay, so I think well, more things to say, but since I'm out of time here.
More questions?
Yeah.
Yes.
sorry, this classification of objects, so can you say a word about its proof? Like I mean, it seems like it's one of the main.
Yeah, so definitely for this first theorem, I do that again. What's the main ingredient? Yeah, there's several steps. So there's a lot of ways you have there's this whole subject of tame representation theory, and people have found ways of, if you have a category which is tame, how to classify its objects. In particular, what you do is in most cases, this category will have some description as a quiver, a graded quiver. A lot of cases, and you get all the other cases by localization. This f of s has some quiver, graded quiver relations description, and the quiver. It's allowed very special types of quivers where you have it also incoming and outgoing arrows. It's like the most complicated situation in the vertex. Where these things could loop back. These relations here should be put adding. It's just saying some product of arrows is 0. And once you have the description, you have some more algebraic problem, and in that sort of formulation is you can prove it. There's still a bit of work to do because it's about a derived category. So a lot of the literature on these tame representation theory is just on they care about modules. Then you need to do something about find some kind of unique representative in each quasi-isomorphism class. But you can do that, and then you can use some techniques. Yeah, but it's very linear algebra heavy. It's not.
But what about the A-infinity structure? I mean, usually these curves have a non-trivial infinity structure.
So there's actually no, it's formal thing. So
No, but the objects, I mean, the objects, like you have closed curves on the surface, usually.
No, but the generators are a complete system of arms.
yeah, you have some formal generators.
It only works on open surfaces.
Right, but the statement is about objects of the category, right? Not the generators. It's about modules over the generators.
Yeah.
And
It's modules over something which has no infinity structure.
We're talking about the modules over a formal algebra. And then the question is, how do you classify the modules?
Yeah, modules over a formal algebra don't have to be formal themselves.
Sure.
That's right.
Right, so they will have infinity structures.
Yeah, but the question is anyway, classification of decomposables. And the question is, you want to show that every decomposable comes from certain geometry, but I have no idea how they do that.
So you get some answer about objects, decomposable objects correspond to some paths on this quiver, and then you can translate this back into actual curves on the surface. But the whole proof is sort of not happening in geometric world, but in linear algebra. Maybe there's some other proof to what you mentioned.
This quiver somehow you fix some kind of system of this quiver just kind of maps between common map between this.
Yeah, so this quiver, this generator is coming from some collection of parts.
So the point is that some kind of line is some intersection.
Yeah. And there's some cases where you don't have this quiver, but there are localizations of these categories. Again, that's good.
So in that case, a stable object you don't know kind of which kind of closed curve, it's just kind of more abstract object. Stable object is this.
It will always be a closed curve. Yeah, that's right. Closed curve. It's one of these objects are stable. With local system, there's some local system.
So given this stability structures, you know the way which slope, which curve is a generator in this stable object. There's some another way to get down.
So yeah, the classification doesn't have anything to do with the stability condition. This is like this.
No, I know, but like, which one is stable? Which curve can be stable?
The ones which are GDC in the flat menu, which have a GDC representation.
It's a just okay.
Yeah.
Yep.
Yeah.
Is there any way of, like any hope of getting this decomposition through some flow as a special Lagrangian study decomposition?
Yeah, I think it should be curve shortening flow. There's some kind of analysis involved in actually proving that, which I think.
what did you call it? Curve?
Curve shortening flow. It's just mean curvature flowing for curves.
So it's two-dimensional, just literally cross that's a good.
Yeah, but you have these singularities and
Other
So if you-
quick,
oh, sorry.
go ahead.
If you go the kind of 4 dimensions, like a K3 or and T4, then you know at least what is the stable object using this hyperkera twist.
yeah.
Then you need to extend this kind without the calculations.
Maybe there's some. I haven't tried that yet, but that's that would be a next thing. That's all these shoots are now generalized to higher dimensions and special Lagrange manifolds with a much more complicated story.
But do you have anything you can say about what you expect the generalization of the half translation structures to be in the case?
I don't really know precisely. Yeah, it's some kind of complex forms. But yeah, it's a bit tricky. I am not sure. What do you say?
Other questions? If not, let's thank Fabian again.